Hi, I'm Mark Perry with Colorado Dam Safety. Welcome back to our tutorial video series on our new guidelines for hydrological modeling and flood analysis. This segment covers section 4 of the guidelines, input data for the CSU SMA modeling method. So this is where we'll start to get into the stepwise procedure. This should go pretty fast. In this video, we'll cover show you where to get all of the input data that you need to run our CSU SMA ArcMap toolbox to estimate basin properties and parameters, and then set up the model in HEC-HMS. So this is input data needed for the CSU SMA modeling method. We'll go through getting the necessary StreamStats data and files, DEM, terrain file, remote sensing, images, the red and near infrared, GNATSCO soil survey, raster files, and lastly, the reps, PMP, and precip frequency design storm files. Okay, so here we are at section 4 of our new hydrology guidelines. I'm working off a draft version, but there shouldn't be any significant changes here when we issue the final version, hopefully later this month. That first section just has explanation of the and kind of a qualifier for the software versions. The research was done in our CSU SMA research, and then the CSU SMA toolbox were developed using HMS 4.7 and ArcMap 10.4.1. And the data sources here, which are largely from USGS websites and then from NRCS for GNATSCO and our reps tools, those may change. And as everyone knows, about the best we can do is just have them current for right now. And then what we say is these guidelines and tools are provided for the convenience of the user to execute the methods that we describe. So the user's responsible for. We will try. Colorado Dam Safety will try to keep the guidelines fairly updated, follow new versions, but ultimately the user is responsible for dealing with changes to new software versions, getting new software versions, finding if USGS links change or options in the tools change. We consider that to be the responsibility of the user. Okay, so first data set we're after is the section 4.2 StreamStats. So I just wanted to show you here that the hyperlinks are embedded in the PDF. So if you've downloaded the guidelines PDF from our Colorado Dam Safety website, you can just click on those and it should take you right to all the relevant sources. I'm going to zoom in here. I'm going to skip through this real quick because I presume that people know how to use StreamStats. So I'm going to skip ahead, and I do want to show what data we need from StreamStats. Okay, so I've just in StreamStats just zoomed in to level 15, and that lets you see the delineated streams. And you do need to, once you get zoomed in, it will ask you to select the state, and you want StreamStats Colorado. Zoom into level 15, we see delineated streams and the location, the point of concentration we want, and I click the delineate option and choose the point, which is at my dam, end of the reservoir for the basin that I'm doing the hydrology study for. So I'm going to do that, and that will take a minute for StreamStats to delineate the basin. Okay, StreamStats delineated the basin. This particular basin is located on the eastern plains on the north side of the Arkansas River in a kind of a complex topography. It's their natural depression topography here, and this basin looks a little suspect, but I think it makes the point that the user needs to check this StreamStats basin delineation, and we talk about that later in the guidelines. Once we download get the DEM, bring the DEM into HMS. We need to review it, and then if needed, we can bring the basin delineation back into ArcMap, edit it based on the terrain, and then if we need to, if it's a significant change, we can come back to StreamStats, and StreamStats does allow the user to edit this delineation, and then we could get revised peak flow statistics. But what we need to start somewhere, so we just start from the StreamStats with the basin it gives us. What we're looking for is the peak flow statistics, a few of the basin properties that will help the user evaluate the reasonableness, and then the basin and point of concentration shape files. Okay, so select out of scenarios, we want to select peak flow statistics, and then basin characteristics. This is really up to the user, but there are some helpful things in using our guidelines, the peak flow envelopes later on when we get to checking the data and making a case for checking the model and making a case for reasonableness. It may help to have the 7,500 foot portion of the basin. I mean, here that's not an issue because we're out on the eastern plains, but it may be in your case. Mean elevation, max elevation. We may want soils, some sort of general soils properties just to help us to make the case for explaining the model results. With that, we could continue, and it was possible we could have already downloaded the basin and point of concentration shape files. I usually go ahead and generate the report and then download them from there. So we'll hit continue, and then that's going to take a minute to generate the report. Okay, here's our StreamStats report. As far as input data for the CSU SMA method for our guidelines, what we're looking for here, the few things we'll need, drainage area. Like I said, some of these basin properties will help us later on in evaluating our model results for reasonableness and making that case. And the main thing we want later on in evaluating the model and then calibrating the model if needed is our peak flow statistics. Okay, so as users of StreamStats will know, the regression estimates for peak flow, the regional regression estimates are by region. So you get each individual region, and then it does an area average. So we're usually looking for that area average estimate, and these are the peak flow statistics, flood frequency estimates in percent AEP. So 1% is the 100 years. So our 100-year ARI or 1% AEP flood estimate for this basin is 9,010 CFS. Okay, so we need that. We will print that report. I'll print that to PDF and I will save it. And I'm going to download the shape files from here. And I want them in shapefile format. And one thing I didn't mention earlier, I should have, is that we recommend you put everything on your local C drive. And that's going to facilitate, seems like that solves a lot of problems with ArcMap and running Arc Toolbox, just having all the data in a C drive. And of course, you can move it later to a server or whatever, but for the analysis part of it seems to work best. So I'm going to put the StreamStats report and the shape files for my input data in an input data folder for this project on my C drive. Okay, the next CSU, the input data we need for the CSU SMA modeling method is the DEM terrain data. So we're at back to the guidelines, paragraph 4.3. And as the guidelines explained here, we need the DEM data to use in HEC-HMS for subbasin delineation and for determining subbasin properties that we use for the unit hydrographs and for reach routing. So we will go to the, again, the embedded hyperlink is in the guidelines PDF. Click on that to go to the USGS national map. We're going to zoom in, and I'm going to use the same example basin, zoom in on the basin area. So remember, we want not just the dam, but we want the DEM for the entire basin. Our area of interest is the map extents here, and then we're going to go down to data, elevation products, 3DEP, and select 1/3 arcsecond. So the guidelines say that in general, 1/3 arcsecond or 10-meter DEM is considered to be adequate for this purpose, for hydrology, basin, subbasin delineation, basin properties, reach properties. But we are going to update the final guidelines based on a subject matter expert review comment that to generalize that to say that more detailed or higher resolution DEM, if it's available, may be appropriate in a case-by-case basis for smaller basins or more complex basins. But in general, we consider 1/3 arcsecond to be adequate, and it's widely available for the entire state. So here we've selected 1/3 arcsecond. We can turn on the show to show that that covers it, but I feel sure that it does here. So yes, we have coverage there. Next then, this is the step that maybe always trips me up, but we need to search the product. So in this upper left button here, you won't get anything if you don't search the products. All right, and so now you see what DEM products are available for this map extents area, and they're generally different dates. And so I'm just gonna take a quick look at those. They're all in GeoTIFF format, and I'm going to select this this top one. You can also look at a thumbnail just to make sure that it covers the basin of interest, and that one may not. Okay, so there's the one we need. I'm going to turn that off again and make sure. So here's our reservoir. This is our area of interest, and it's this DEM. So this is going to be the one that I'm going to add to my cart. Going to go to the cart, get that one, and then download this in TIFF or GeoTIFF format. It's a large file, so it'll take a minute. Again, we're going to emphasize that we recommend putting all this input data on your local C drive. You can organize it similar to how the guidelines are organized in input data, and then we'll have the following sections for subbasin properties, basin parameters, model. But our recommendation is to keep these files on your local C drive to facilitate the analysis in ArcMap. It just seems to solve a lot of problems. Okay, the next input data we need for the CSU SMA modeling method is Landsat red and infrared band images. They call them B3 and B4. We're here in the guidelines in paragraph 4.4. So we need this in order to calculate a raster image, a gridded data set of fractional vegetative cover. And that's used later on to adjust infiltration rates based on vegetation cover. And this is similar to the vegetative cover adjustment, or it is the same vegetative cover adjustment that was done in our previous guidelines. This process had, during our kind of initial trials of this modeling method, our peer review, and our internal tests, I would say this process caused the most problems. I want to emphasize here that this is offered as an option. It's not a requirement. If people have a better way or another way they want to estimate vegetative cover, in order to do that adjustment to infiltration rates, loss rates, then that's, the other methods may be acceptable if they're documented and justified. But this is meant to be an automated and consistent or reproducible way of analyzing vegetative or calculating vegetative cover. It's not something that we particularly want to get too bogged down in. It is really, as we've said in our previous tutorials, the entire modeling process is really considered a starting place, the parameter estimation method, and then the model results have to be evaluated against the observed flood record and then calibrated is described later in the guidelines. So this could be the vegetative cover can be looked at as just another variable in that, and then it could be go into confidence and possible calibration or adjustment later on if the infiltration rates don't seem reasonable. So just to say, to not get too overly bogged down in this, it's really meant to be automated, fairly easy, and after you've done it a few times, and consistent or reproducible. Okay, so if you want to get this Landsat imagery to calculate vegetative cover, go to, again, the embedded hyperlink here to USGS Earth Explorer. So we hop there, and we're going to, you need to log in is the first step. If you don't log in, you're not going to be able to download products. So if you don't have a login, it's going to give you the option to create one. I'm already logged in here, so I'm good to go. Now, next thing we're going to do is I'm going to zoom in on the area of interest. I'm going to move to this location that we've been doing out on the Eastern Plains, the same example basin here. And I'm going to do my search criteria up in these tabs above, and I'm going to just use the map for that, and it's going to define this new area of interest based on the map coordinates. Okay. Next thing I'm going to do is then progress here down to bottom to data sets. Okay, and I would go, this is already dropped down, but I would go down to, the first time you go through, you'll go down to Landsat and expand that. I'm going to go down to either Landsat Collection 2, Level 2, or Level 1. The guidelines currently say Level 1. I think we sometimes have better luck with Level 2. You can Google that. There's lots of information online about the difference between them. It's a quality difference, and Level 1 is higher quality, but Level 2, maybe in being more general, it seems to give better results in certain places anyway. Or you can play around with both of them and see which works better for your site. But we do want Landsat 4.5, and then so this is Category 2, Level 2. I'm going to check that. Then we're going to go to additional criteria. And what we want to do here is specify the cloud cover. You don't want an image with a bunch of clouds in it, and in Colorado we're pretty lucky that way. So we're going to select 0 to 10% cloud cover, and that will just filter out our, use that as our search criteria. And the satellite, we want Landsat 5. So we did we have experienced some problems with using Landsat 4 images, so I would recommend, the guidelines recommend using Landsat 5. Okay, with that, we can proceed to results and see what products are available. And the three things we're going to look at here is the date. So that's the date of the image, and then the path of location, path and row here, and then we can get a thumbnail showing where it is. Okay, so if we're this was my area of interest, and so we can see that this one that I just selected does not cover the area of interest. There's the next one, and those are the same path and row, so 31, 34, so we're going to have to find a different one. Okay, so that looks better. So I want that, path 32, row 33, and now I'm going to look at the date. And what the guidelines say is, so we're using this for fractional vegetative cover. So conservative would be more towards, late fall. I mean, I suppose even winter, although we don't want snow cover. But in terms of less vegetative cover, I guess we're saying the end of fall, September, October could be a conservative approach. Another approach that we discuss in there is then to look at the seasonality of reps design storms or the storms being analyzed, and we refer you to later sections in the guidelines that talk about reps storm seasonality. So you could go to the reps PMP tool, gives the dates of historic controlling storms, and the reps Met Portal precip frequency gives histograms, the reporting, and in our current guidelines here, we give histograms for storm seasonality by storm type. You can look at controlling storm types. You could look at historical floods, peak flows in the basin, or just anecdotal, whatever history of flooding you have there, and see what's applicable. Is it April, May flooding? Is it June thunderstorms? Is it July, August monsoon? And so you could use that type of approach to select the remote Landsat imagery that's closest to that season or date of time of interest. Okay, so I'm going to pick this one here. It's October, but using that first criteria I talked about being fall here, it should be a conservative approach. I've looked at the footprint, it's the right image, and then I'm just going to download that. It's going to give me product options and what all we're interested. We don't need this entire bundle. All we're interested in is the B3 and B4 images, and those are the red and near infrared images. So you can see those are already at least is 50 megs each, so they're still big files. We're going to download each of those, and that will take a little bit of time. So B3 and B4, and again, just like we did with the other input data, once I get those downloaded, I'm going to put them on my local C drive into a project folder under input data to facilitate use in ArcMap in the next step. Okay, the next input data set that we need for the CSU SMA modeling method is the GNATSCO raster soil data. So this is percent sand clay, organic matter, and then depth to restrictive layer. So this is, we're in section 4.5 of our hydrology guidelines, soil property raster data sets, and we're talking about the NRCS, Gridded National Soil Survey Geographic Database, or GNATSCO in acronym terms. Okay, so again, we got embedded hyperlink here, and in this case, this is not. It takes you to our Google Drive, not to the NRCS website first. That first link, because CSU, when they were doing this research, they downloaded the GNATSCO files, and then they went ahead and mosaicked them in ArcMap to create single raster images for each soil property of the entire state and the tributary areas of Colorado, everything we would need. So we provide those for the user's convenience at your own risk, and then you would just this is our FTP Colorado DNR FTP. So you would just select those and download them. It's a lot of files. So it's about 900 megs, pushing a gig of data there. So it'll take a little time. The good news is this is a one-time deal. So this covers the entire state. What I would recommend in this case is putting these on a local C drive and in their own folder, and then these files would be used for every project you do in using this method in Colorado. So it should be a one-time deal. Now, a couple words about that. The guidelines talk about the units. So here we have percent sand, clay, organic matter, raster files, and those are in percent. So they are percent of each of those uh, uh, soil types, and then the depth to restrictive layer comes in units of centimeters, and those are the units that those files will be input into the CSU SMA Python script to calculate basin properties and parameters. And then if you do not want to use our mosaic rasters, then the guidelines also just provide, for convenience, the link to the NRCS website, so you could just go there yourself and download the data that you want to do through this for this gridded for your site, for the gridded National Soil Survey Geographic Database. The last input data we need for the CSU SMA method is our design storm data, which we get from our Colorado Regional Extreme Precipitation Study tools, or REPS tools. There's two of them, the REPS PMP evaluation tool, or just PMP tool, and then the REPS Met Portal precip frequency tool. So this is in the our new hydrological guidelines for hydrological modeling and flood analysis, but there's a link to our separate guidelines for use of the regional extreme precipitation study rainfall estimation tools. Again, an embedded hyperlink in the guidelines PDF that'll take you directly to that document, and then that document has links to download the REPS PMP tool, which is an ArcMap toolbox, and then to hyperlink to the REPS Met Portal precip frequency tool, which is a web service. Okay, the thing we need to talk about here is area sizes for partial area analysis, and that's discussed in more detail here in the hydrology modeling guidelines than it is in the REPS, the actual REPS guidelines, because it has more to do with our subbasins, and once we set up have a basin and subbasin delineation, area sizes and things. So, but the REPS tool, the REPS reports and the REPS tools have area size limits by storm type, which correspond to the historic size of these storms, or storm size statistics, the spatial area patterns by storm type. So we have this table 3 in our hydrology modeling flood analysis guidelines. The top shows REPS PMP storm area size limits. Now, REPS PMP tool, these are essentially guidelines or recommendations. The tool will run for any area size, but the recommendation is to limit 2 and 6 hour local storm PMP to 100 square miles. So in other words, if your basin's 500 square miles, it would be inaccurate to get a smoothed out 2 or 6 hour local storm PMP estimate smeared out over that entire area size. That's just not how these storms occur. They occur in 100 square mile or less cells generally. So in that case, you're going to be wanting to do a partial area analysis, and that's generally going to be a partial area, lowest elevation, nearest to the dam or reservoir of interest. But that could vary on case by case, but it's the partial area, 100 square mile partial area, that would give the worst case flood for this storm type. So 24-hour local storm, the hydrology guidelines here recommend referring to running the PMP tool, seeing what your controlling historic storm is. Say if it's Cherry Creek, May 1935. And then you go to Appendix F of the REPS, and I'll show you how to do that. Volume 2, Appendix F, and it shows DAD curves. How big was that storm? You can get an idea of what the actual area size was of your controlling storm for PMP, for your basin. And then for 72-hour general storm PMP, there's no size limit from the REPS PMP tool. These are large-scale synoptic storms, large area sizes. For the second part of the table here is the REPS Met Portal for precip frequency. These storm area sizes are based on stochastic analysis that consultant did on historical storm spatial patterns for each storm type. So they're a little different, but the same idea. The REPS Met Portal precip frequency is broken up into geographic regions: east, Rio Grande region, and west. They each have 3 storm types: 2-hour local storm, 6-hour MECs, 48-hour MLCs, and each of those have a corresponding area size. Now the difference here is these are actually are related to the stochastically generated aerial reduction factors that MetPortal uses, applies to the point precip frequency estimates. It applies an aerial reduction factor to get a watershed precip frequency estimate for your basin. Now, if you exceed these size limits in MetPortal, it will not return a watershed precip frequency estimate for this the given storm type. If you the given storm type where you exceed the area size limit. So if you have a 300 square mile basin, you run the MetPortal tool, it will not return this 2-hour local storm because there is no aerial reduction factor above 200 square miles. So again, you have to, then you're looking at doing a partial area analysis. We get a partial, a part of the basin that corresponds to as close as possible to this limit size, and generally lowest and closest to the dam or reservoir. Now, this tip talks about that in practice, the way to do this is to delineate your subbasins in HMS first, because your subbasins in HMS, you're going to enter these reps rainfall time series as precip gauges in HMS, and then you're going to assign those precip gauges to individual HMS subbasins. So it only makes sense to delineate your subbasins first, and then essentially accumulate those or consolidate those to form these partial areas of the size that you need for reps. Okay, so this is a bit of a chicken and egg, that we don't talk about the HMS subbasin analysis, basin delineation, subbasin delineation until Section 5 in the guidelines in our Section 5 tutorial. So what I'm going to do is jump around a bit here, and I'm going to go over it quickly here and then refer you to the Section 5, the guidelines and Section 5 tutorial for a lot more detail on HMS delineating subbasins. So just a quick preview. I'm going to go over the HMS subbasin delineation really quickly. So for now, I'll just ask you to believe me that we delineated these subbasins for our, this is for our example basin, delineated these subbasins in HMS using the DEM and stream network that HMS generates. And then we can export this through GIS, export layers, export this subbasin shapefile, and we're going to bring it into ArcMap, and we're going to combine these subbasins to form our 2 partial areas that we need. So for our example basin, the StreamStats told us that the basin area was 249 square miles. Again, we may not exactly agree with this basin boundary from StreamStats, but it is a starting place. So 249 square miles. Going back to the Hydrology Guidelines, we see that we know we have a 100 square mile area size limit on the reps, 2-hour, 6-hour reps PMP local storms, and then a 200 square mile on the MetPortal precip frequency 2-hour local storm. So we need 100 and a 200 square mile partial area from this that's less than our 249 square mile basin. Okay, so we export this subbasin shapefile. I brought it in to ArcMap and did some analysis, which is thoroughly covered in the Hydrology Guidelines Section 5 tutorial, but it basically amounts to selecting certain of these subbasin elements from the shapefile, extracting those, making a new shapefile, and then dissolving those, and some cleanup work to clean up these stray lines, and then it ended up with 2 partial area shapefiles. So one is this lower, about 100 square miles. It's 107 square miles. That's for the PMP tool. Remember, the PMP tool, it's not a strict limit, it's just a guideline. The second partial area is around about 200 square miles, and that's for the reps met portal precip frequency, 2-hour local storms. Now that one, remember, is a strict limit. It will not return an answer for a watershed precip frequency estimate if I exceed that 200 square miles, or that whatever that area size limit is. So in this case, I checked it, and it is, in fact, a little close to, but a little less than 200 square miles. Okay, so now we're going to be able to use these two partial area sub-basins, partial area analysis areas in our reps tools to get our design rainfalls. First, I'll show you the reps PMP tool. So hopefully you've downloaded that. If you haven't, go to that reps, the guidelines for use of our reps tools, and it has a link to a FTP in Google Drive or Google Drive to download the reps PMP tool. It's an ArcMap toolbox. So if you know where you have that, you go open Arc Catalog. Inside ArcMap, drop down your reps PMP tool folder until you get to the evaluation tool, and there's a script folder that houses the actual tool, and just run that. Okay, now I'm going to start with the 2 and 6 hour local storm and partial area analysis. Okay, that's the sub-basin or areas, partial area shapefile that I'm showing on the screen now. Remember, our larger area, our entire basin is this larger area. We're going to start with the local storm partial area analysis. So we select from the shapefiles that are loaded into our project this PMP local storm partial area. Okay, this is the location of the PMP tool. The output folder, I'm going to go ahead and put that in my project folder for this example project. I'm going to create a new folder called reps PMP. Okay, now we're only doing local storm analysis right now based on this partial area, based on a local storm area size limit. I have to select a minimum of the 1 and 2 hour and the 6 hour. So those three durations are used to construct the 6 hour local storm. So we're going to get returned here for the partial area. We're going to get 1, 2 hour, and 6 hour PMP. Okay, and we're going to get importantly, what we want is the 2 hour and 6 hour temporal patterns, which is what we're going to use in HMS. Or you know what, we could go ahead and run the 24-hour duration. If you recall, that's the area size limit there is going to be based on historic storms, controlling storms. We might as well go ahead and run it at this 100 square mile partial area, and then we'll see if that corresponds approximately to the size limit of the controlling historic storm for this 24-hour PMP. Okay, we do not need to run general storms. We're going to run that for the entire basin area, 249 square miles. Okay, and we don't need to run tropical storms. We'll need to check whether tropical storms are even applicable to this basin. They're only applicable below 38.5 degree latitude. These other things we'll just leave as defaults and hit OK. That's going to run. Now I want to make a point here while it's running that this will be I'm showing you a complicated case where we have a large basin and we need to do partial area analyses in reps PMP tool and the precip frequency tool because of reps area size limits. Okay, if your basin is smaller than say 100 square miles, this is going to be much easier. You're not going to have any partial area analysis. You're going to have your single basin. You'll probably delineate sub-basins in HMS for other reasons, which are talked about in the Section 5 tutorial and the guidelines, but those would be for just basin physiography for other reasons, and not necessarily reps area size limits. So in that case, you just have a single basin shape file, which you would run in the reps PMP tool, run all the storms, and then the reps precip frequency tool, run all the storms, download your design rainfalls. So I'm showing you a difficult case. We've completed our reps PMP tool analysis for the 2 and 6 hour and 24-hour local storms. I wanted to get back to that tropical storm issue. This basin, I checked the basin is below, it's south of the 38.5 degree latitude, so we will run the tropical storms. But the point here, there was that we don't run it for this partial area. Tropical storms and general storms do not have an area size limit in the REPS PMP tool. Okay, so we're just running 2, 6, and 24-hour local storms. Let me hit on, before we go to the results, let me hit on an issue here. So the question might be, do you want to run the REPS PMP tool with these sub-basin elements in the shapefile? And if you do, you're going to get separate the REPS PMP tool can handle sub-basins in shapefile. But if you do that, you're going to get separate PMP estimates, more of a distributed PMP estimate from the, the REPS tool generates a gridded raster of the PMP estimates. So it can aggregate those any way that you want it to. So it can give you separate sub-basin PMP estimates. Mostly that's not warranted. That's going to be extra work. It's going to if you use that data, you're going to want to create a separate precip gauge for each sub-basin in HMS and assign those separately. That's for more of a fully, or a more distributed hydrology analysis. Most cases, we feel like that's not warranted. You just need a uniform rainfall unless there are major differences that you would expect. So the case we talk about more in section 5, when we're looking at the sub-basin delineation, is if your basin crosses a major REPS climate region. So generally the biggest one is at 7,500 feet along the Front Range, where the typical scenario would be the dams out on the plains and your basin goes up into the mountains. In that case, you are going to want to create a separate area for the lower part of the basin in, say, REPS transposition regions 1 and 3, plains and foothills, and then a separate area for, transposition zone 5, the mountains. And then you have a basin shapefile with 2 subbasins, and REPS PMP tool will return a separate PMP estimate for each subbasin. If you run it like this, it will still base the reduction from the data from the depth area duration curves on the total basin area. So it's a valid PMP estimate for the entire basin, but it differentiates for each subbasin that you have in your shapefile. Okay, now the MET portal tool will not do that. MET portal tool only returns a watershed precip frequency estimate for the entire basin shapefile. Okay, all right, so with that said, let's go to the REPS PMP tool has finished for our partial area that we ran. Okay, so it's just this 100 square mile, approximately yellow, lower partial area in our larger basin. All right, and so you can scroll through in the REPS PMP tool. It does give you some dialogue as it goes, the messages, and you can scroll through those, especially if you have a problem. But we didn't, and we'll close that. The next thing that we're going to do is add the data. So we're going to go to the Add Data button in ArcMap, and we created this REPS PMP folder in our project input data. Remember, I just wanted to say again, this stuff generally works better because this is an ArcMap tool. It generally works better on a local drive. So I have everything in a local C drive at this point in a project folder. Okay, so we created a REPS PMP folder on the local C drive, and the REPS PMP tool creates a local folder, and when I run general and tropical later, it will create general and tropical folders. So that's where it puts your rainfall data. Okay, so if I open this geodatabase, it assigns the name to the shapefile that we ran, PMP LS PAA. It's our partial area analysis, and it gives it the area, square mile area. I open that, and you're going to see your gridded rainfall data. You're going to see a basin average attribute table, the points shapefile, which has all the information about the historic controlling storms, and super helpful, and then the actual temporal pattern. So in this case, we were in for the 2, 6 hour, and 24 local storm PMPs. Okay, so what we can add that just to show you what they look like better much with the gridded data. Okay, so here it all is. Let's now turn off our basin areas. I'm going to leave that partial area on, but take off the fill so that we can see it. Okay, so there's our partial area that we ran. This is our gridded 24-hour PMP estimate, just as an example for you. Okay. So 24-hour PMP ranges from 13.4 to 14.7 inches. Okay, I'm going to turn that off. I'm going to show you the other output. We have the point file. This contains a wealth of information for the different durations, 1 hour, 2 hour, 6 hour, 24 hour. It gives PMP amounts at each point. So if we select one of those, it's at an actual grid point for the analysis. Okay, it gives the SPAS storm number, which is the historical storm number that is in the REPS database, and then for layman's terms, it also gives the historical name, location, center, and date for that controlling storm. So for this cell that we've, or this grid point that we've selected, the 1 hour controlling storm was the Hale, Colorado, May 1935 storm, and fully maximized and transpositioned. That gave, at that cell point, that storm gave a 1 hour PMP amount of 6.4 inches. Okay. Now the tool also gives our basin average PMP. That's just all these points averaged over our 100 square mile partial area here. So 1 hour averaged, aerial average uniform 1 hour PMP is 6.26 inches, 2 hours 9.65 inches, 14 inches. And what we're really after is these temporal distributions, and we're going to export these. So if we open these, this is going to give us our time step and our PMP amount. So a temporal pattern for the storm, which is what we're going to put into HMS as a precip gauge, okay, for each storm type. Now, the 6 hour, 2 hour only has one temporal pattern. 6 hour has three. What the REPS guidelines recommend is using this 6 hour synthetic temporal pattern. So once we export this and go to import this into HMS, we want to use this last column, 6 hour synthetic, in this case east, because this basin's in the eastern part of the state. And the 24 hour also just has one temporal pattern, so that's easy. Okay. So I want to go back to, before we export those, I want to go back to this point attribute file, and we said we were going to look at the 24-hour storm. I want to see controlling 24-hour storm. I want to show you how to do that, to look at more details of that storm. Now, this storm can vary by location at each point. Each point could have a different controlling storm at that location. But in this case, it's pretty uniform. There was this Holly June 1964 storm, which was a giant storm. It had the 24-hour rainfall record for Colorado for a long time, until the 2013 storm, which set it at Fort Carson, southwest of Colorado Springs. But this was a big storm at the 24-hour duration, so it ends up controlling over this entire partial area. So if we want to see how big the area of that controlling storm, the area size, we can then go to the REPS summary reports, look up this Holly 65 storm, and we can use this SPAS number, if that helps, 1293-1, and we'll look at the DAD table or charts and see how big the storm was. We'll use the guidelines for the REPS tools, which is on our website. As I described previously, just open that reps tools guidelines, and then if you scroll down in that, and you will get to a link for the full reps study documentation. It'll take you to a Google Drive, volume 2, and within that you'll see Appendix F. Now that's a big file, 80 megs. I've already opened that, and it's a long file, 760 pages. It's organized by general storms, then hybrid, then local storms. But this Appendix F, Volume 2, gives all the documentation or background data for all the historic storms that were used in the REPS PMP analysis. So we said that we found from our point attribute file from the REPS PMP tool outlet for output for our basin, the controlling 24-hour local storm PMP for PMP was this Holly, Colorado 1965 storm. So I went down in Volume 2 Appendix F, found it, and we have a bunch of information about it, the description, some of the confidence ratings on it, and then we have the DAD table. Sometimes there's a table of the temporal pattern at the storm center, wherever we best have it, shows synoptic scale or larger scale, weather maps, whatever information, high split moisture, upper and lower level, moisture supply to that storm, various other information. But what we want to look at right now, the point of this was to go back to a 24-hour storm and look at the area size of the controlling storm, because that's what the guidelines say, talk about as far as area size. Look at this historic controlling storm and see what area it had. So we don't want to be too awfully far off of that. Now, the area goes out to whatever, 40,000 square miles. But if we look at this, the depth area duration curves, we can kind of see where the bulk of the rainfall was. In other words, where the storm center was. So it areas out to about 100 square miles, which is convenient. Based on our partial area, 100 square mile partial area, we had about the bulk of the rainfall. Once we got outside of that, then we start to see essentially an exponential decrease in the amount of rainfall out to these larger area sizes. I mean, it was clearly a big, probably MEC, larger scale storm system, covered a lot of the state, but the bulk of this center occurred. The main part of this storm center, this Hale, Colorado, or Holly, Colorado storm center occurred below 100 square miles. So I think it looks like 100 square miles for our partial area analysis. It was a pretty good area size limit for that 24-hour local storm. So we'll go ahead and stick with that for our 2-hour, 6-hour, 24-hour REPS local storm PMPs. Now going back to ArcMap, we'll go ahead and export these temporal patterns, and we'll export all this stuff while we're at it, but we mainly need these, or definitely need these temporal patterns to put into HMS as precip gauges. So we just right click on each attribute table, data export, and again put them into our project file. I would say it's a good place for them, and I put them in text file format. It'll be easy to put into HMS, and we can just call this reps. This is our 2-hour local storm temporal pattern. Don't need to add that, and then we do the same thing for the 6-hour and 24. We'll have those, and then I'll go ahead and export this basin average shapefile and the point shapefile. We'll talk about, in the next section, we're going to talk about some reporting, and we'll want to go ahead and put those in the reports. And we actually want to print a map of the local storm PMP as well, just to show further reporting, just to show the spatial variation. Okay, and then the next step for the REPS PMP tool would be getting the PMP data would be to run the tool for the entire basin for the general storms. Before we do that, let me revisit this issue with the StreamStats drainage basin. So by when I talked about the partial area analysis, I mentioned that we jumped ahead and did the basin delineation in HMS from the DEM and from the HMS's stream network that it identified from the DEM. That's covered in detail in the Section 5 of the guidelines and the Section 5 tutorial. But I'd mentioned when we downloaded StreamStats, the flood frequency estimates and the shapefile, that may not, we're going to want to check that. So the blue basin boundary is the shapefile from StreamStats. The red is from HMS, delineated from the DEM and HMS's stream network. So the fact is we want to check both of those and make sure we agree with the basin boundary. Now I went through this, like I mentioned, this example basins on the eastern plains, north side of the Arkansas River here, and it's some complex terrain. There's depression topography up here. It's a bit of a plateau and then eroded landscape down to the river. This is flat land, and I zoomed in here, so I'm checking it against a 24,000 scale USGS topo map. Just to get some idea of what's going on here, the discrepancy. And if I zoom in here, this is really depression topography, really complex drainage. And I could probably go either way, but I tend to side with the DEM that it's looks like these pits and depressions may all be draining into this adjacent basin. So I'm going to go, in this case, with the HMS delineated basin. We exported that from HMS, then I dissolved it in ArcMap and got rid of the sub-basins. For reps purposes, we're just treating this as an entire basin. So let me get rid of the stream stem, and now we're going to return to the reps P&P tool to do our general storm and tropical storm analysis based on the entire 200 and whatever. It's a little, StreamStats said it was 249, so we're a little less than that, I believe, about 237 square miles from the HMS delineated entire basin. Now remember, again, this was a complicated case I showed you where our basin exceeds those reps storm area size limits, so we had to do a separate partial area analysis for the 2, 6, and 24-hour local storms. Now we're doing the entire area analysis for the general and tropical storms. Hopefully, in most cases, you won't have that. You'll just have a single basin, say less than 100 square miles. You'll just run the reps tool once for all the storms. But in this case, we're now going to pick the entire basin, and again, we're going to give it the output folder on our local C drive. I'm going to skip the local storm analysis. We already did that for the 100 square mile partial area. I'm going to skip down to the general storm. The only durations it needs in order to complete the temporal pattern for the 72-hour general storm is this 24, 48, and 72. So we can save some time by not running those other durations. We don't really need those. Same thing for the tropical storm. Since we're south of 38.5 degrees latitude, we need to run that. Need to select at a minimum 24, 48, 72-hour durations. Go with all these other defaults. Hit OK, and the reps P&P tool is going to generate those general storm and temporal and spatial results for us. Okay, the reps P&P tool finished our analysis of the general and local storm, general and tropical storm P&P. So we're now going to add that output data to our project, and we're going to export it for our use in HMS and for reporting. So we'll go up here again to add data, and I just want to show you that in that reps P&P folder, the reps P&P tool creates this general and tropical folders itself where it puts all your output. Okay, so let's just go into general, for example. Again, it creates this geodatabase which has all the output in it, so we can get the actual gridded raster, P&P raster, shows the spatial pattern, and then we can load up the basin average attribute table, the point file that gives all the historic controlling storms at each grid point, and the temporal distribution, which is what we need, attribute table, which is what we need to create a precip gauge in HMS. So we'll go ahead and add those, and then again export all of those just like we did with the local storms. So I want to show you, we just export this temporal pattern, for example. Again, I put that in text file format. That'll be the easiest to work with. So put that in general. Easiest to work with in creating a precip gauge in HMS. So this is reps 72-hour general storm, and that's their temporal pattern. Export that. Not need to add it, but I want to show you something here if you're not super familiar with ArcMap. For the points file, we want to export that. It's going to be, we want to see it for the reporting. But when you have a when you have a shape file, you have to, and you want to export just the text, you have to open the attribute table. These data files like the temporal pattern are already attribute just tables from the reps PNP tool. But we have this point shape file. We have to open the attribute table showing the tabular data, and then once that's open, we can export that as a text file, and that's what we want to see for this point file to show all the controlling historic controlling storms at each grid point. Okay, so now we can export that to a text file, and I would just call that reps 72-hour general storm, and that's just points. Okay. Okay, and again, that's going to show you is controlling historic storms at different durations at each grid point in the basin. Okay, do the same thing for tropical storms, and then we're finished with reps PNP, the reps PNP tool data, in terms of the input data we need for the CSU SMA, our CSU SMA modeling method. The last step is going to be getting the reps Met Portal precip frequency data, and then we're finished with all our input data. So now for the precip frequency estimates for our analysis, we go to the Met Portal, reps Met Portal tool, and it's the web service. You can, if you don't have this link saved or don't know where it is, you can start again with our guidelines on our dam safety website. The reps rainfall estimation tool guidelines, open that, and that has a link. And when you click on that link to the Met Portal tool, it's actually going to redirect you because there's a new version of that. But just click on this link to be redirected to the new version, and you're going to go to Met Portal version 2.20. Click here to begin. Okay, so what we're generally interested for any hydrology watershed analysis is this second tab, watershed precip frequency. Okay, and if you recall, we have a large basin, about 240 square miles. It exceeds the area size limit, a strict limit here for the local storm, 2-hour local storm precip frequency. So that affects the size limit, applies to the stochastically generated areal reduction factors. In other words, the reduction factors, reduction in precip frequency that they saw by running statistics from a whole bunch of historical spatial patterns. So it's limited for local storm, simple convective thunderstorms, 2-hour, the precip frequency is, watershed precip frequency is limited to an area size of 200 square miles. So that's where we created our partial area shape file. It was about 195 square miles, close to that 200, but not going over. Okay, so we're going to pick this local, we're going to start with that partial area analysis, the local storm 2-hour partial area analysis. We're going to upload a shape file, and we're going to pick that partial area shape file. So here it is, and we need to grab all the 6 files, component files that make up an ArcMap shape file, and those will load into Met Portal. And if it does it correctly, you'll see that show up as the basin on the map. And yes, we see that, and then we can zoom into it, just check, make sure it came in the right place, and there it is, our basin, lake, or our reservoir Lake Meredith and Dam and our basin. Okay, so now it automatically shows us the precip frequency, 2-hour local storm precip frequency, watershed precip frequency estimates. This was the mean of the point precip frequency estimates. Then it gives you the area reduction factor calculated from our roughly 195 square mile partial area, and then applies the area reduction factor and gives us our best estimates, or ARF reduced watershed precip frequency estimates for each AEP from 1 in 10 to 1 in 10 million. Shows us a precip frequency curve, and then we want to typically show the uncertainty bounds on those. We can plot the reps PMP, and it will overlay it as a horizontal line on our precip frequency curve, which we like to do. It's a great cross check, useful for checking PMP results, reasonableness. Okay, and then we can download the data. So we have several options here. What we want is download the data, and this is going to give us our 2-hour precip frequency estimates. And typically in the reporting, we're going to ask you to also do a screenshot. Not a super finished report here, but it's fine for what we need. We're going to ask you to have the precip frequency curve table and a screenshot of the map showing that you've imported the correct basin, or what the basin you used is, in fact. So if you just do a screenshot of that and include that in your reports. Now, what we really need, again, for HEC HMS, what we need is the temporal patterns. So after we've done that, got that output out, downloaded the data, we go to temporal patterns, and we do the same thing. We need the 2-hour local storm. The watershed file is already there, and then we can pick a AEP multiplier just for the plots. I'll pick 100, 1 in 100, or 100 year, and then the storm of interest. So this is the storm. There's example historical patterns it can use for a temporal pattern, but we typically, with our reps guidelines, recommend using the synthetic storm. So that's what we want to do. The 2-hour, in this case, 2-hour local storm synthetic pattern, and it's going to apply the precip frequency estimates for 2-hour to that synthetic storm temporal pattern. We want all AEPs, so this is storm type. For this 200, roughly 195 square mile partial area, we have 2-hour local simple convective local thunderstorm, storm type, all AEPs, and the synthetic storm pattern. We download that data, and that's what we need to create our stream gauges for HMS. Precip gauges in HMS. Now, the last step we're going to do is we're going to use the full basin, come back and load the full basin in, and then do the same thing, same process we just did, the precip frequency curves, and then the temporal patterns for the other 2 storm types, the 6-hour MEC and 48-hour MLC. Okay. So let's go through this one more time, just using the 6-hour MEC precip frequency storm type as an example. So we're back in Met Portal. I would recommend if you're using a different area. So we're using a different shapefile this time, because for the 2-hour local storm, we'd use the partial area shapefile, less than 200 square miles. Now for the MEC, 6-hour and 48-hour MLC, we're using our full basin area, which was just a little bigger. But again, that's a strict limit that the local storm precip frequency will not be generated if you use a basin shapefile over 200 square miles. So now we're going to use a full basin area area shapefile for the 6 hour and, well, the MEC and MLC precip frequency analysis. Okay, so I'd recommend closing out a Met portal, reopening a new session of it, and then loading in a new shapefile. Okay, so we're going to do MEC 6 hour, and we're going to go down, go to watershed precip frequency tab, and we're going to go MEC 6 hour, and then we're going to upload our shapefile back to our project folder, and I'm using this HMS subs dissolve. Okay, a couple points I want to make about this. Let's flip back to ArcMap. And HMS, I talked about that we kind of skipped at the section 5, and we used HMS to delineate a more accurate basin with subbasins and the partial, combine those into the partial areas that we needed for reps partial area analysis. But the point I need to make here is this HMS, that we used the HMS basin because it was different than StreamStats, so I felt like it was more accurate. Usually, in most cases, the StreamStats basin is going to be fine for reps analysis, but in this case, this was a complex depression topography, and so I used the HMS basin delineation. But the Met Portal tool do not use these internal subbasin elements. I think if that confuses Met Portal, and I don't want you to get messed up there. So what I did was dissolved that HMS subbasin shapefile into just the basin boundary, and that's just by using ArcMap, the Arc Toolbox, data management, generalization, and dissolve. So I end up with just the outside basin boundary with no internal subbasins. That's what I want to use in Reps Met Portal. Okay, so that's the file I loaded. Now that's our full subbasin, or full basin now, the 237-ish square miles, whatever it is. We're going to use that for 6 hour and 48 hour precip frequency. So I'm going to again say show uncertainty bounds. This is the watershed estimate we talked about. The ARF is in there. It shows the precip frequency curve with 90% uncertainty bounds at 5% and 95%. So this is a 90% bounds here. Shows precip frequency estimates for 1 in 10 to 1 in 10 million. And I'm going to overlay this REPS PMP just to show you what that looks like. So from our REPS PMP analysis, we got that basin average PMP text file. We exported that. That lists one local storm, 1 hour, 2, 6, and 24 hour. So the 6 hour is this third PMP value, 12.73 inches. So that's the number that we want to put in here is always going to be the analogous duration. So we want to put 2 hour REPS PMP in. We're doing 2 hour precip frequency, 6 hour, 6 hour, and the 48 hour general storm REPS PMP, or tropical storm, 48 hour tropical storm REPS PMP, when we're doing a MLC 48 hour precip frequency analysis for comparison. Okay, so now it Met Portal plots that PMP on as a horizontal line, and that gives us some indication, just a cross check, reasonableness check of where REPS PMP lies in terms of precip frequency. Great way to do an independent check. These are two independent methods, PMP, deterministic PMP versus probabilistic precip frequency. So we can see here our REPS PMP plots out at about 10 to the minus 7 AEP. That's very reasonable, maybe where we should be, okay, or where we'd like to be. All right, so now we're going to go ahead. I'm going to go ahead and do a screenshot of this for the reporting, and then I'm going to go up. With the map showing the basin. And this is the full basin again, and then I'm going to go up here and download the data. Then I'm going to go to the temporal patterns again. Select 6 hour synthetic storm. Let's go ahead and do that. 6 hour. Again, the basin shapefile is still loaded, so we're good there. And then we want to just pick an example. This is just for scaling the plot here, 1 to 100. and then selecting a storm. So here we have front and back loaded synthetic storms for the 6-hour MEC. So we're going to use the guideline reps. Just look at the reps guidelines to tell you which synthetic storm to use. The guidelines say, reps guidelines say to use the front loaded synthetic storm for a 6-hour. Select that. It's going to plot up the temporal pattern, and then we're going to select download all AEPs and go ahead and download that. All right, let me just jump to that folder and show you what this output looks like. So the output we want to see from RepsMet portal is going to be, like I said, a screenshot of that map showing the basin you used, the precip frequency table with uncertainty bounds, PMP plotted on it. Then you're going to download the temporal patterns of the precip frequency data. That's going to give you this temporal pattern plot. It's going to give you a temporal pattern CSV file. These are going to be each AEP, and it's actually written in terms of ARI, 10-year, 100-year, and then it goes out 1,000-year, 1,000-year, 10,000-year, what have you. And it tells you here what region we're in. This is for the 2-hour local storm. Temporal patterns, we use the synthetic storm pattern to get these temporal patterns. Minutes, time in minutes is here. And then I'm going to wrap this and show you what's here. Okay, this is incremental. It's got 2 columns for each AEP or ARI. One is in incremental and inches, and the other is in accumulated inches. I generally use accumulated inches, but I just know that they're both here, and you can do either one in your HMS precip gauges. Okay, so you get that. As far as the temporal patterns, you'll get an image of the precip frequency curve, 2-hour, and then a table of the precip frequency table with upper and lower, the upper 90% confidence bounds, best estimates, the watershed average point estimate, and the ARF. So that's output from Met Portal. Lastly, we would do the 48-hour with that full basin, and let me just do that here in the temporal patterns tab to show you what the storm patterns, temporal storm patterns are. Again, the full basin shape file is still loaded, so we're good there. Just pick an AEP to scale to, and here we have backloaded and center loaded. So the guide, and this is for the East Macro region. These vary by macro region. Our example basins in the East Macro region, we're going to pick that center loaded synthetic storm. And again, the guidelines, guidance on these storm synthetic temporal patterns is in the REPS guidelines document. So look to that if you have questions. Download all AEPs and we'll download that. So we'll get results for 2-hour local storm, precip frequency results, 2-hour local storm, 6-hour MEC, and 48-hour MLC. Finish the section 4 tutorial here. Just as a recap, this is section 4 of our guidelines, our new guidelines on hydrological modeling and flood analysis. So this was on the input data, covered the input data needed for the CSU SMA modeling method. All right, so we went through getting the basin boundary and flood frequency estimates from StreamStats, got the DEM terrain data from the USGS national map. We got the Landsat red and infrared band images from USGS Earth Explorer. We got our soil, percent sand, clay, organic matter, and depth to restrictive layer soil rasters from our Google Drive or from NRCS GNASCO. And then finally, we got all of our REPS design storm data from our REPS PMP tool and REPS Met Portal precip frequency tool. And we talked a fair amount about partial area analysis, where your hydrology study, your basin, runs up against the REPS storm area size limits. And like I said, that was a kind of presenting you with a worst case, so you'll see what to do if you have that. If hopefully, if your basin, probably the majority of basins are going to be less than these area size limits, and you'll just be able to have a single basin and run the reps tools and get the PMP and precip frequency design storms. Okay. We talked about if you need to do partial area analysis, that you're really going to skip ahead to HMS to go ahead and do your sub-basin delineation, and that's going to be covered thoroughly in the next tutorial. So thanks for joining us for this section 4 input data tutorial, and the next one, section 5 of the guidelines tutorial, is going to cover then how to load everything into HMS and delineate basins, get all your basin properties needed for reach routing, for creating unit hydrographs, and then getting into ArcMap and running the CSU SMA Python script to generate all our basin properties, which are then needed to generate all the model parameters in the following section. Okay, thanks. Join us for the next one.